Welcome back, everybody. Happy LDOC. In this last lecture, what we're going to do is connect the lab you've been working on with the concepts we've been learning more recently, the system calls for controlling, creating, forking, and piping to processes. Right? So if you have not completed the lab yet, I would encourage you to postpone these videos. These videos are going to assume that you have a working parser and scanner. So let me just give you a demo of what we expect your problem set to look like at this point in its evolution. So we've got a prompt for our parser. If I run a simple command like lslah that has 2 word tokens in it, we see that we get back printed out from the parser's main file, the command text, right? We know that this was actually a command node under the hood, and there's only a single node in our parse tree for this example that's made up of many words in a string vector, right? But if we were to run a slightly more interesting command like lslah piped to, say, grep for C files, we would see that we have a tree structure, right? And so at the root of our tree, we have a pipe node, and that pipe node has a left-hand side, which is the lslah command, and a right-hand side, which is the grep end of string followed or preceded by a C command, right? And so if we were to add an additional output here, like grep C, and let's say we had a ton of files, so we only wanted to show the first few of them, notice that this tree structure is recursive, and we can pipe one command into another piped command, right? And so here we see that lslah is being piped into another sequence of pipes, and we've got quite a bit of complexity here, right? So when we start imagining what this tree could look like. So if we wanted to visualize this in this first simple command here, we know that we have just a single node in our tree of type command, right? Or a command node, right? And that's the root. Whereas in this next example, so this was just the lslah. In the next example where we piped lslah to grep foo, what we had was a pipe node at the top, and it had a left-hand side child node of a command node and a right-hand side child of a command node. And what we're going to try and do in this lecture is bring home this project such that given these various kinds of inputs, how can we write some code that will take this structure of what it is that we're trying to do, right? This conveys some desired outcome that we want the computer to execute on our behalf using fork and exec function calls. And how do we translate or interpret and execute these given command structures in actual system calls that will bring it to completion by the operating system. So when we're faced with a challenging problem like this, and this is a general tip when trying to confront problems for the first time, it's best to start with the simplest case, right? Especially when you're faced with recursive problems, you're best off starting with the base case of a recursive problem. So rather than worrying about, well, how the heck are we going to implement something that executes a pipe, right? And runs multiple commands, forks multiple commands, pipes them together, connects all their inputs in the right way. It feels like there's a lot of complexity there. It turns out there's not a great deal of complexity if we structure our problem right. But what we're going to focus on first is how do we just get to the point of running a simple single command and set up some structure that will allow us to evolve it from our effectively our base case towards being able to handle a recursive execution pipeline where we're piping one command into another, right? So we're going to get started on just this simple problem in this video, and then as we move towards the full piped implementation, we'll add on in another video, right? So the first thing I want to do is start a file to hold the logic or the code for our execution engine, right? So I'm going to press Control D here to end my input. I'm going to clear my screen, and I'm going to start a file named include exec.h, right? And we're going to go ahead and do the if def or if not defined exec h, define exec h, right? And so this is our include guard to make sure we don't include this file more than once. And I'm going to go ahead and have my endif so I don't forget to. And we're only really going to define one top level API function here. The rest of, we will break this problem of executing nodes down into multiple functions. But at the top level, the API, at the barrier of abstraction that we care about here, we are just going to define one exec function that you give it a pointer to a node, and it carries that out. It executes that node's contents as if you were trying to evaluate it for processing by a shell. Now we get an error here that says, hey, we don't know what node is, so we need to be sure that we include the node.h header file here so that we have a declaration for what node is, or a definition for what node is. All right. So now what I'm going to do is open up another file. We need to go provide the implementation of this file. All right. So I would encourage you to go ahead and get your exec.h header file set up. And then let's go work on an exec.c file after this. All right, so I'm going to open up source and exec.c. And the first thing we'll do is include exec.h. All right, so that gives us our header declarations. And the function that we declared was void exec node pointer node. Right? And so the purpose of this function is to execute whatever command nodes or pipe nodes that are given to it. Right? So first, we should probably figure out, are we dealing with the kind of node we want to be dealing with? So let's switch and test whether or not the type of node we're dealing with is actually a command node. So the command node, remember, is just a simple single command. And if so, we'll do something and we'll break. Otherwise, for now, let's have just a default rule here. We'll need to handle piped nodes in the future, but we'll leave that for once we care about them. We're going to try and minimize the code we write while we're sort of scaffolding out, making sure we can get this just a command node to work. And I'm just going to printf to do and break. All right. So we're going to see that we have an error here because we don't have standard IO included. So I'm going to go ahead and include standard IO. And I also have an error because of this colon rather than a semicolon. Got to be careful about that. Okay. So, okay, we've got a switch statement. What are we going to do with this command node? Well, rather than try and define the exact logic inline here, what I want to do is dispatch off to another function that handles a command node specifically. So we can start to break down our problem of processing these nodes into functions that are a little bit simpler than trying to put it all in one, right? And when we get to a piped node, we'll want to do something similar as well. So let's go ahead and set up a helper function. And I should declare that as static so that it's only defined inside of this particular C file. And we're going to execute a command node, right? It's once again going to receive a pointer to a node. So this is the prototype or the declaration of this function. And now let's provide an implementation of it. All right, so exec command, and we're going to give it a pointer to a node. All right, so what do we do here? Well, remember what our node has if it's a command node, and we know that it is because this is a function that's private to this particular file. And the only place we're going to reach this from, in fact, let's go ahead and make that call. We're going to exec a command node, and we're going to give it this node. Right? So at this point, we know and we have some guarantee that, hey, this is a node whose type member is going to be command node. And it's going to have a in its union of what its node value is going to be the words string vector, right? That are the actual arguments that we want to start this command with. All right, so when we go to execute a command, what do we want to do? Well, what we learned in the last lecture is that we want to fork a child process and then execute a command in that child process, right? So why don't we go ahead and fork here? So I'm going to say if fork is equal to, and then what is the ID of the forked child? Because we want to do something special with a child. It's 0, right? Well, 0 is a magic number, and we should probably put a name on that so we can remember what it is we're looking at here. So I'm going to go ahead up at the top and define forked child constant, and its name, its value is going to be 0. All right, so I'm going to jump back down to line 23 and go to 0 and replace that with 23. Oops, not 23, with forked child. All right. So we've removed that constant that was a magic constant. And now we have another error that we're being told we need fork, right? So where does fork come from? We need the Unix standard header file, right? And so fork is defined there. We only care about fork giving us back a child instance here. And for the purposes of illustration in today's lecture, we're not going to handle error cases for forking and piping. Generally, it's best practice that you should. And in fact, that's a good exercise to go back and properly do. Remember, fork would return -1 if we could not fork a process, so we would need to handle that case. In this case, if it doesn't return 0, then we're going to see that we're not going to do much. We're not going to do anything at all. But it would be nice to have an error message or something and be thoughtful about how we handle errors. But we're going to think about the primary paths through the program as we illustrate the fundamental concepts of how a shell comes together. All right, so we forked a child, and now what do? Well, I'm going to leave it to future us to try and figure out how do we get our data for the actual command we're running out of the node value that we've been given as the command node that we're processing. So let's start with something simple and hard code in the command that we're going to evaluate here. So I'm going to set up a variable, and it's going to be the argv variable, and it's going to be an array of character pointers, right? So we're going to have an array of C strings here that is just going to be the string ls and then the null terminating string for reasons that we talked about in the previous video, right? And then what we'll do is execute this command, right, with execvp, which was the system call we looked at in the previous lecture. And execvp will take over this child process and run the ls command. And we're going to give it argv0, which is the ls command, and then the argv pointer array as the second parameter, right? And so these two values then will be passed to the execvp system command, and this will spin up an ls process, right? So no matter what command we actually type in, what we're saying here is we're, for now, just going to try and blaze a little bit of a path that we can expand upon and start to improve upon as we just convince ourselves that this code even works in the slightest bit. All right. So because execvp never returns, right? And we're going to assume this works again. Again, you should have error handling here. We're being a little bit, we're throwing caution to the wind. It's LDOC. We're living on the edge. And so what we're going to do is assume and trust that this works. And if so, that means that once we get out of this, that if then else statement, we're definitely in our parent process, right? And so for now, we're just going to wait on that child to complete, right? But we need to import the wait function, and this is in the syswait.h header file, right? So we've got an exec function that will dispatch off to exec command, and this will spin up a simple little process for ls. And now we need to go reconfigure our main program to dispatch out to this exec function, right? We want to actually call exec with some parsed node pointer, right? So I'm going to split screen here, and on the left-hand side, I'm going to open up source main.c, all right? And this program is going to be where the last bit of helper code that we gave you that emits output for parsed node trees. And we need to make a few modifications to it. All right, so let's think about this read command or this read function. Rather than having a command line prompt of parser, let's change that to be thsh. All right, so this is going to be the Tar Heel shell, right? And this is our prompt. And read otherwise is fine. It returns to us the number of bytes that were read into this string line pointer parameter, right? And so after reading, we are then evaluating this line, right? So eval was a little bit funky here. Eval was written such that it returns to us a node pointer that was our parse tree, and then print it out, right? So let's go ahead and to minimize the number of changes we need to make, what we're going to do is call exec here. And so rather than printing that parse tree, we're going to execute that parse tree. So we need to include our exec.h header file. And again, rather than printing the parse tree, we're going to exec that parse tree. And we can get rid of that print statement, all right? And so now what's happening is we read our input, we evaluate it by reading it into a parse tree, and then we go and we execute it, right? Rather than printing it. And because of the way process execution works, when we spin up that child process, it's going to have a handle on standard out. So it will still print its outputs to standard out. We don't need to explicitly print anything from within our shell program here. All right, so let's try this out. Make run. So now we see this thsh prompt. And if I give a command like ls, what do you know? It looks like it works. But if I give a command like echo, well, remember we hard-coded that ls command in there, but it looks like things are coming together, right? We at least have some confidence that our loop is running. We're spinning up a child process, the ls process. We're dispatching off to it, and we can continue giving commands, right? So I'm going to press Control D to end my input, and okay, we've updated our main function such that we're dispatching our execution or control off to our exec file. And this file is now responsible for executing a parse tree, right? So currently, this is what we would call like a minimum viable program for being able to continue to make progress on how we execute, right? We still have work left to be done here, but this is generally a strategy that I would encourage you to take when you face other problems in other courses, in other professional experiences. Try and find the minimum path that's required to get you from where you are to just a proof of concept that allows you to make more progress, but starts to have the structure that you need in order to continue doing so. All right, so the first thing we should do is get rid of this hard-coded execution of ls, right? What we want to do is take this node pointer that we have and read the arguments and the command out from its vector of words, right? So if we backtrack here just a little bit and we think, well, okay, what are the words that we're working with in this command? So I'm going to set up a strvec pointer to words. And this is just going to be a reference that we're getting a handle on the node's word value, right? Because if we say node data.command, remember that command is the strvec of words, but we really want the address of it, right? We're just trying to get a reference to it, right? So we now have a vector of strings named words that this was, you did the work of parsing these words out in the previous part of the lab. So what we really want to do then next is let's figure out how do we get this arg values array to contain all of the pointers to all of the C strings that are contained in this string vector data structure, right? So let's set up a size t variable that is going to be our argc or arg count, and this will be the strvec length of words, right? So this will be the number of words we have in our string vector. And the next thing we're going to do is say, okay, well, let's set up an array for this. And how many elements does our array need? Well, argv here, notice that when we had only the command word in this hard-coded command, we needed 2, right? Because we needed not only space for a pointer to the initial command, but also to a null value that allowed us to terminate that list of pointers in the system calls eyes, right? So we need argc +1 entries in this particular argv array that we're setting up. But we can't hard code these values in. Right? What we need to do is actually assign those values one by one as we iterate through, or we move through each of the indices of our words vector, right? So just for good measure, and to be sure we don't accidentally overwrite, or we don't forget to make the last value of this argv array null, let's go ahead and handle that case where we're going to say argv of argc is 0, or I could say null, which is the end of arguments, right? And the next thing that you need to do, and I'm actually going to turn this over to you for a moment to remind yourself how to access elements in this words string vector, is I'm going to leave a to-do here, which is fill in argv with pointers to the C strings stored in our words strvec, right? So that's loaded, but I want you to try pausing the video here and effectively writing a loop that accesses the strings stored in words, and then those strings, remember, are smart pointers, which contain not only the length of the string and the amount of capacity of the string, but then a pointer to the string's value on the heap. And that string value on the heap is the C string value that you want to fill in this argv with pointers to, right? So there will be a couple of steps here. And what I want you to try doing is just writing that loop to assign references to each of those argument values, and then resume the video once you're done. All right, so let's write that loop together. Hopefully you were able to do it. And when you compiled, it would have given you the ability to run arbitrary commands that were simple. You can't pipe yet. We haven't implemented piping, but you could have run a simple command. Right, so let's write this for loop. So I'm going to say for size t I is initially 0, while I is less than argv. That's the number of values in our words list. And we're going to increment I by 1 each time, right? So we've got our usual suspect for loop here. What we're going to do is set up our ultimate goal here is to assign to argv I some string value. Okay. But we have to jump through a few hoops in order to get that pointer to the C string that we want to assign to argv, right? So how do we actually get the pointer to the array of byte characters that is the C string that we're going to be passing along? Well, we've got our words strvec, and so why don't we set up a variable that accesses the specific word at index I, right? So str pointer to specific word that we're accessing is going to be the result of strvec referencing the words strvec and index I, right? So what we're saying here is we're setting up a pointer that's temporary that is going to reference the word at index I in our vec of words that came into us from our node, right? And then what we want is to get a reference to the first character in that word. Well, you all implemented as part of the str class of functions a function named strref, and we give it a word and index 0, right? And so that gives us a pointer, or the address of the index 0 character of that word string, and we're assigning it to index I of our arguments values, right? So we clean that up. And what we did here was we effectively just set up an array of char pointers that we could pass off to exec VP, right? And I just realized, based on this error message, I accidentally wrote argv instead of argc, right? So argc is the count of the number of values that we have, whereas I had previously accidentally written v instead, right? So argc is the size t variable we set up. That's the length of our words. All right, so let's try this out. So I'm going to make run, and now if I run the ls command, we get correct output. But if I run ls-lah, notice we get different output. And we've actually run this ls-lah command giving those arguments to it. If I said echo hello world, notice that we're spinning up a child process and calling the execvp function, giving it all of the correct arguments it needs based on how we parsed this input. So we've actually implemented a very simple shell here that can execute single commands one at a time, right? And waits for those commands to finish. So another example would be, let's say cat/user dict user share dict words. And what do you know? Like all of those words are being piped to our terminal, and we kicked that process off through our thsh shell. All right, so that's pretty awesome. We've got a working, very simple shell. Doesn't have piping yet. Doesn't have input-output redirection yet. In fact, that part of the problem set or lab is going to be left to you if you want to implement it over the summer. I would encourage you to. We're going to get to piping next, but I do want you to take a moment to consider how cool it is right now that we are running. You wrote a program here at this point that is a shell, and it is making the commands to ask the operating system to run some other process, and it is parsing those commands and turning it into an actionable sequence of steps.